that can take the high temperature. But you also need to make components that possibly have cooling chambers, that possibly have the ability for water cooling or other types of cooling. And as a result, something like additive manufacturing becomes very useful. You can create complex components with cooling chambers or so by additive manufacturing. So this is where the benefit really can be. So you can see that now the one of the elements that are available due to cost and in general they have relatively good irradiation performance. Again, tungsten appears among all of these materials as one of the very few that can behave and can take those harsh conditions, alongside being an element that doesn't get activated, it doesn't get, when it hits by the byproducts of nuclear fusion, it doesn't get activated, meaning that it still remains generally safe to handle even after irradiation. So tungsten, what do you know about it? Tungsten in general has potentially the highest melting temperature of all metals that we know. It has in general good thermal conductivity. It has low tritium retention, which is an issue that we are worried about in nuclear fusion, because in that case we are using heavy hydrogen atom, tritium atom, essentially to combine and eventually form helium. And essentially it's a good material because it does not retain it inside it, that which may embrittle it, in fact, later on. It also has a low physical sputtering yield and a good combination of high temperature strength, good creep resistance and good tensile strength. But on the negative side, in general, as I showed you, it has poor oxidation resistance. So this might not be an issue when you are doing a fusion case. So it's not too bad, because in fusion we don't have that much oxygen anyway. In general, it's a BCC structure, a body-centered cubic structure. And we know that body-centered cubic materials are in general very brittle. They also have that very, very poor weldability. And this is essentially an important criterion to know that we can use it for additive manufacturing or not. If you can't weld it, it's highly unlikely that you can use additive manufacturing to make it. Furthermore, it has a fairly high ductile-to-brittle transition temperature, which means that if you are below 400, which is quite a high temperature, the material behaves in a brittle fashion. So that's really a problem, because in additive manufacturing, things will have to cool down. And as they cool down to temperatures below 400 or so, and there are lots of residual stresses, there is a big chance that cracks can open and defects can form. Finally, it's very sensitive to impurities. Oxygen, carbon, and other elements, they actually deteriorate the properties quite rapidly. I found some references that look into that, and they all go back to the 1960s and 70s from early work from NASA. So for instance, you look here into the first one, ductile-to-brittle transition temperature. And you can see that additions of oxygen or carbon will increase the ductile-to-brittle transition temperature, which is bad news, because in additive manufacturing, we are handling powders in oxygen, most likely, even if you're using argon in a powder bed machine, you still have some oxygen, you have a very large surface area. So you're likely to increase the ductile-to-brittle transition temperature in a polycrystalline tungsten, these two lines there. And that accordingly will get the material to be in a brittle fashion below those temperatures. But let's look into the numbers. Now, this diagram shows the influence of oxygen content on the ultimate tensile strength of tungsten. The first plot, which seems nice, where you have a fairly high tensile strength and then it drops gradually with temperature, this is the case for 4 ppm of oxygen, 4 parts per million of oxygen. Whereas if you look into 10 parts per million, which is the square, the material is embrittled only by 10 parts per million, 30 parts per million, which is the diamond, and then the triangle is 50 parts per million. So we're really facing a mission impossible here, because we're trying to create a component using powders, potentially through an atmosphere that may contain some residual oxygen, even if it's using argon. And as a result, whatever you make is likely to become a brittle component. You're unlikely to get a material that is not brittle. You can see that the strength drops approximately by at least a half or so, around a 1/2 quickly with the addition of oxygen. Now, this is another case of comparing clean tungsten with tungsten after welding. And as you can see, this is the impact test, or essentially it's a bend test, but it's also used as a way to look into it as a ductile-to-brittle transition temperature test, like an impact test. And as you can see, in clean material, the ductile-to-brittle transition temperature is around 150, let's say. But then after welding, where you pick porosity, where you pick oxygen, where you pick all sorts of inclusions, the ductile-to-brittle transition temperature moves into much higher temperature, meaning that the material becomes brittle at even higher temperature, not cold temperatures, as you know in BCC materials. Again, that's a similar figure to the previous one. It shows here the oxygen content and how it changed from 4 parts per million to 10 parts per million to 50 to 30 to 50. And again, we're looking here into the reduction in area during mechanical testing. And as you can see, oxygen additions is in general bad news, something that is not good for the mechanical properties of tungsten. So how do people try to fabricate it? In the probably around 3 or 4 years ago, the main, prior to 2015, most of the people used powder bed machines, laser powder bed fusion machines that had powers that go up to 200 watt. And that was in general quite low. So most people realized tungsten printing through mixing tungsten particles with a binder. In that case, it's material like copper or nickel or iron. And what you do is that when you melt these elements together, that the nickel or copper or iron are going to melt, and they are going to essentially act like a super glue adhering to the tungsten particles, creating what we call in that case a tungsten heavy alloy. So you are basically just using those elements to get things to stick together in such a way. But with the advancement of the higher temperature machines, like higher laser power machines like the ones with 400 watt and higher, that was able to melt tungsten, which I'll talk about in the talk. So that in a sense started to work, but the problem here was that you created cracked pure tungsten bills, which was not, I would say, a surprise. We knew that this is a material which is very susceptible for oxygen pickup, and it is very susceptible to, it also has potentially a higher brittle to ductile transition temperature, and as a result, it's likely to crack anyway. Now, some recent studies, which is like the one I'm going to talk about today, try to look into adding minor alloying elements to act as oxygen getters. In that case, people started to alloy tungsten with elements like yttrium or tantalum or lanthanum to create dense crack-free builds, which is what I'm going to talk about to you today. Now, in parallel to laser powder bed fusion, there are other groups that looked into the wire and arc additive manufacturing process. In this case, use basically a wire of tungsten and use a welding technique to create a pure tungsten wall, as you can see. You can, in a sense, create a wall. Yes, you can deposit tungsten, you can create a shape, but if you have a good eyesight, you might be able to see there's a nice, lovely crack extending across the wall. Again, it's the same problem. You're likely to get cracks. You're likely to get anisotropy. You're likely to get all sorts of potential problems. There are cracks there. You can build a wall, but as you know, the wire and arc technique is limited in what it can do in terms of the geometrical complexity. It cannot make a very complex shape. So why did people find in the early studies, why did they find, in the case of powder bed fusion specifically, why did they find that the material cracks? The main theory comes from the fact that when the material solidifies, typically the dislocation front would move, and because oxygen has a very limited solubility even in tungsten, that oxygen is going to be segregated to the grain boundaries, or segregating, in this case, as you can see, into the center line of the melt pool. And oxygen in that case acts as an embrittling element, and it will crack the material. And that was what many people found, that the cracks happen along the grain boundaries. The main reason is that is the oxygen. When you have the oxygen inside the material, that will eventually lead to crack formation along the grain boundaries. And as you can see, the cracks propagate in such a way that they are all intergranular cracks. So what can we do? I mean, in Birmingham, we started working on tungsten in 2014, and that was through a collaboration with a company called MIME Material. MIME, they manufacture X-ray collimators. So this shape you see in front of you is a device or a piece made out of tungsten. It has, as you can see, holes. These holes are around maybe 1 or 2 millimeter in diameter. The aim of the collimator essentially is that you block X-rays and you keep, or not block X-rays, actually keep X-rays to go in certain directions. They are used in medical X-ray devices. They're used in radiotherapy type devices where you use X-rays to treat cancers, for instance. Now, typically that would be made out of a block of tungsten, and then you would be drilling the holes individually. And of course, if you get one hole incorrectly, you scrap the entire part. So John Patterson, who's a colleague from MIME Material, he came to my office one day and he gave me essentially a small bottle of tungsten powder. And he said, can you try to print powder, to print that material? And I said, yes, we can print it. Let me try. So we tried. And you're able to get, as you can see in that micrograph, in general, it is dense. You don't see much pores, but you obviously can see cracks. So there is between grain 1 and grain 2, there's an obvious crack here. There is an obvious crack there. So the material is cracked. When I told him that the material is cracked, he was like, I am not bothered. Because in fact, although it is cracked, it still can perform its function. This part is only there to block X-rays and get them to pass in certain directions. So as a result, I don't really need mechanical properties. It's not even exposed to any mechanical loading. So as such, it does the job. And that was, in a sense, a great moment because MIME Materials, they filed the patent on the SLM of tungsten. And then the product now is launched in the UK market. And they also paid me for the development of this work, £200, which is probably around $250 by today's prices for my consultancy on this project. So you can see that it did end up being a commercial product at the end, although it is cracked, although it is defective from if we think about it as a material science point of view, but it does the job. But so one of the good things is that we've used our concept laser machine that we have in Birmingham. The machine has a fiber laser, of course, 400 watts, and it has a build envelope of 250 by 250 by 280. But we have modified the machine since we got it by adding into it a reduced build volume. So we can actually build with very small amounts of powders. We have a substrate that is 50 by 50 millimeter, so only 5 by 5 centimeter. And then we have another substrate which is 10 by 10, and then another substrate which is 20 by 20. So I keep telling people, if you get me a cup full of powders, we can actually process the material and make a go just at processing it. We also modified it by having a heated substrate. So we added cartridge heaters into the substrate. So now we can heat the substrate up to 600, 700 degrees. But when we do this, the heated region is only around 60 by 60 millimeter. We cannot really heat the entire substrate. Only a very small section can be heated during the process. So the key, I would say, contribution we made to that work was when we looked into how we can get the powders to behave and how we can look into helping them with powders. So if you go in the market nowadays and you want to try to buy tungsten powders, you can buy two options. You can buy, on the right-hand side, the chemically reduced powder, which is made by HC Stark, or now it's called Tynaiobis. That powder is, as you can see, it looks like flaky. It has faceted particles inside, and that's because it's made by chemical reduction. And then there is that powder, which is a spherical powder. That's made by a process called plasma spheroidization, where basically the powder to the right-hand side goes through a system called the Tecna plasma spheroidization system, and that will convert that ugly-looking powder into that nice spherical powder. It's a little bit coarser, but in a way, it's just a conversion from this type to that type. Now, the question that we had was, which one of them is better? And it was a very important question because the HC Stark powder costs around £50 per kilo, whereas the LPW powder costs around 150 pounds a kilo, almost 3 times the price. So the key question was, if we are making that component where we're not bothered if we have some cracks, we're not bothered even if we have some porosity, as long as we can block some of the X-rays, as long as the part has some reasonable mechanical or structural integrity, which one of them can we use? So what we did with that, we compared both particles, and as you can see, the powder that comes out of chemical extraction, it has a lot of fine particles, and those of you who work on additive manufacturing, they know that having too much fine particles is not always great. Whereas the plasma spheroidized, as you can see, was very nicely sieved between 20 and 50 microns. The apparent density was high, which is also good in reducing your defects. If your apparent density or your TAD density is high, that means that the powder is nicely packed in the chamber, and that usually results in high density eventually in the build. Both powders were found to flow all right. There is no issue about their flowability in general. Not too bad, I would say. Interestingly, the oxygen content of the faceted powder, the irregular shaped powder, was lower than the oxygen content of the spherical powder. And if you remember the numbers I was giving before, 170 and 370 means that regardless of which one you use, you're going to get cracks. This is way too high than the level that the material can take of oxygen, and you're likely to get grain boundary cracks. But it's more importantly that we look into why does it matter. I mean, you can see that the powder morphology, of course, will affect the flowability, as I explained. It will affect the packing density of the powder in the chamber. Lower packing actually means that fewer particles are in contact, so it affects the thermal conductivity in the chamber. Lower thermal conductivity also will reduce the melt pool depth, so it will reduce the level of remelting, which is ideal in the case of additive manufacturing to ensure that the microstructure is homogeneous and that the layers are essentially attached to one another. The morphology even affects the laser absorption. So even if you have, in that case, actually, the irregular shaped powder is better because that will allow multiple reflections of the laser, whereas the plasma spheroidized one will reflect the laser. That's an interesting aspect between spherical and non-spherical particles. And usually powders which has low laser absorption, they require high energy input because there is some reflection of the laser, or back reflection of the laser is going to happen. Now the question is, did it matter? That's the key point I have for you. So we have kept when we did the processing, we kept the laser power at the maximum, 400 watts. We used the standard island scan strategy for the machine we have. And as you can see, we had to go into very low speeds to get high density, around 8%, really, really low speeds. So, and the part itself, when tungsten is melting, it's glowing so high that you have to wear safety goggles to watch it as it's being processed. Now, you can get approximately 98, as I said, density with the nice spherical powder, whereas with the non-spherical powder, you are getting around 90%. Let me show you how they compare. So now these are the two powders. This is the irregular shaped powder to the left-hand side, and this is the nice spherical powder to the right-hand side. And for the same parameters, you can see that this one has some cracks, some porosity, whereas this one has more porosity and cracks still. Let's look into another condition. Now this condition has, some porosity, as you can see here, and some cracks. This is the one made by the spherical particles, whereas the one to the left-hand side is the one made by the irregular particles. Now, when you show this picture to the company, or when you showed them to M&I, they were like, well, it doesn't really matter, does it? I mean, there's only a slight difference in density, or there is a difference, I'm sure, but it's a slight difference in density. And in a sense, again, if that part doesn't take mechanical loads, if it's there to block the radiation, then actually that one, which is cheaper, which is 1/3 the price, is potentially okay. And that was, I think, the key contribution we made, and that's where reality is in additive manufacturing. We can try to seek a material that doesn't have cracks, doesn't have pores, best quality possible. The question is, we sometimes end up over-designing what we want. If we need a structure that is only there as a shield against the X-rays, then we don't really need to increase the cost of the process by using the high-spec powders to do the job which is required, which can be done with the low-cost powder. So yes, I mean, we can get some conditions, as you can see. You can see fairly dense. Yes, we do have the cracks, but again, fairly dense, good density, but with some cracks. And cracks, as I mentioned to you, they do form at the edges of the melt pool. So this is a melt track, as you can see on the EBSD map, and you can see where the cracks are forming. It is indeed because of the fact that the oxygen gets rejected into the melt pool boundaries, as you can see all around the melt pool boundaries, and also in the center of the melt pools, and that leads to the formation of cracks. Now, this is where that we tried a little bit on the clever bit, and this is the part that made a significant difference. So there is a theory for alloy design which relies on a concept called the E/A ratio, the electron density, the electron valence electricity per atom ratio theory. Essentially, the E/A is the ratio of the valence electron per atom. So if you're talking about elements like tungsten, chromium, moly, vanadium, and so on, tungsten, chromium, moly, they have a valence electrons of 6. So that means that the E/A is 6. Whereas vanadium, tantalum, niobium, they have a valence electron of 5. So each alloy that you make has an overall E/A number. So for instance, if you do a calculation of, let's say if you have an alloy which is 50% tungsten, 50% atomic tungsten, and 50% atomic tantalum, so 50% of this, 50% of that, that means that that alloy has an E/A ratio of 5.5, which is the midpoint between the two. Now, a very important paper by Stringer and Rosenfield from 1963 said that there is actually a transition in the solubility of oxygen in materials. So, and that happens at a ratio of 5.7. If the E/A ratio of the alloy that you're processing is greater than 5.7, oxygen is insoluble and it will form oxides basically. Whereas E/A, if it's less than 5.7, oxygen can be dissolved in solid solution. In a sense, the idea is simple. There are elements that, if you forget about the numbers and how accurate the numbers are, the message is that if you want an alloy whereby you don't want the oxygen to be loose, essentially, and you don't want the oxygen to be insoluble or so, then you just basically add one of these elements. So if you alloy, let's say, tungsten with tantalum, you might be able to get away with that and avoid having oxides formation. And that can mean that the oxygen can be dissolved in solid solution to some extent. So just as for the sake of the exercise, let's say, if you want, for instance, if you have an alloy of tungsten and yttrium, so if you add an alloy of containing 92% tungsten and 8% yttrium, that is going to give you an E/A ratio of 5.6. So this is an alloy that is essentially going to be not susceptible for cracking because oxygen can be dissolved in the solid solution. And again, if you want to go a little bit, so if you look into the tungsten tantalum, for instance, if you're doing almost 5842, that's a 5.6. If you want a tantalum-rich alloy, that's 5.2. If you want a tungsten tantalum alloy, again, that will lower it to 5.9. Now, these alloys are all interesting and everything, but the way that we choose alloys for additive manufacturing for fusion is rather interesting. So this is a section of the transition metals in the periodic table. So usually the way that we do when we talk to people from the nuclear fusion sector, we tell them, well, we think if we add this element, this will go to reduce the crack. And then they say, well, no, but you cannot use this element. You cannot use that element. Usually all the people who work on fusion, they have a periodic table like that, where essentially the elements in green are okay. So these elements are fine. They can work with them in a fusion environment. And then you have the elements which are in yellow, which you can work with them in, depending on the design, we call it in a medium activation condition. And then there are elements which are in medium activation, the orange ones, which they don't like, simple terms, they don't like. And then we've got the red ones, which high activation elements, which they don't like at all. So elements like niobium, moly, nickel, copper, aluminum, they never want them to be inside a nuclear fusion environment. Whereas yttrium is okay, zirconium is okay, tantalum, of course, is okay, tungsten is okay. Rhenium is not among the favorites, but it's also not favored because of the cost point of view. So the way we've done it is that we said, okay, we're going to try to work on a tungsten tantalum alloy. Now you look into the phase diagram of the tungsten tantalum, and it's very nice. The two elements, they love each other. They form a solid solution between them, which is really nice. And the material has also the liquidus temperature is, well, essentially it just transforms from a single phase unlimited solid solution. And also from a point of view, the tantalum has an oxide, which is the tantalum 205, which is the one appearing here on Ellington diagram in the blue line. This is the tungsten oxide, WO3. Now the tantalum oxide will form more readily than the tungsten oxide, meaning that if there was excess oxygen, tantalum would happily suck it. Tantalum would happily suck it and will prevent it from going into the tungsten. So the idea is simple. If you make an alloy of tungsten and tantalum, two things. First of all, the tantalum will form the oxide. Second thing is that the tantalum addition will increase the capability of the solid solution to absorb some oxygen into solution, which in theory means that cracks should not form. That's the overall theory of the whole approach. So that's the point. Oxygen solubility in tantalum is around 200 parts per million, whereas it's 1 part per million for tungsten. So adding a bit of tantalum might help to reduce the cracks that we saw before. So the way we did it in the initial investigation, we simply did in-situ alloying, whereby we had tungsten powders. We blended a lot of tantalum into it, and then it was about 10% weight percent tantalum was added to tungsten, blended with raw emerging before LPBF fabrication. And we did we looked into the density difference. And as you can see, adding the tungsten alloy on its own, maximum you can get is over there. Whereas when you add more the tantalum, you start to densify a little bit more. You gain an extra maybe 0.5% or so by adding a little bit of tantalum into the material. But to try to understand what actually happened, we needed to use XPS, X-ray spectroscopy, spectroscopy, to look into what happens in the microstructure. And for those of you who don't do XPS, I just put a slide to explain what XPS. It's a technique used to understand the composition of the surface of the material, because we wanted to know how do they differ, what actually caused, what will be the microstructural difference between the two. And the way it works is that you are using X-rays that are directed onto the surface of the sample, and you're getting characteristic electrons out of it, which then can give us an indication about the surface condition and the type of elements that are present, the chemical state on the surface of the material. So the observation we saw, here is the difference. Striking difference, as you can see. Pure tungsten, horribly cracked, as I said, between the melt pools, grain boundaries, cracks that extend. You see this is 200 microns, so we're talking about long cracks, very long cracks. Whereas when you add a tiny bit of tantalum, the cracks are all gone, completely gone. You don't see any cracks. And when you use XPS, now XPS was applied to be able to map the system, to look into why does it look like that, what is happening there. And XPS showed that when you map the grain boundary, so that's a grain boundary, and we found that this was oxygen enriched. So the white line there is an indication of oxygen enrichment. So it does prove the point that the oxygen enrichment here happened on the boundaries that eventually led to the cracks forming. Whereas when we looked into the tungsten tantalum, you cannot see significant, obviously you don't see cracks. You see some dispersed oxides. The slightly bigger spheres are porosity from the additive manufacturing process, but the tiny small ones are dispersed electrons. So key point is it did work. Tantalum acted in two ways. One of them is that it increased the solubility limit of oxygen in the matrix of the tungsten tantalum alloy. Second thing is that it acted as a getter, so it sucked all the oxygen, creating a dense crack-free alloy using that simple approach of just adding a small amount of tantalum while still keeping the alloy fusion compatible. So what else can be done? Well, we can, refractory metals in general, we can print many refractory metals, and we've done previous work printing, for instance, vanadium. So this is vanadium alloy, which we know that you can print confidently. It prints really nicely, in fact. We have printed chromium with levels of, poor success, with no success actually, with chromium and molybdenum. Both showed massive cracking. We printed more recently niobium, and niobium seems to print quite nicely, even if you start from faceted powder like that one. In general, among all the refractory metals I covered before, tungsten with tantalum addition, tantalum on its own, vanadium on its own, and niobium on its own, they all print nicely. Molybdenum and chromium, we struggle a little bit with their printing. So what else can we try? What we can try is that people may know the one of the things that people have been trying, especially among the research groups that have access to this ability, is having hotbed powder bed fusion machines. So this is a paper that's probably one of the very few papers that looked into this. This is a paper by a group in Fraunhofer Institute in Germany who used a heated bed machine. Essentially, that machine can heat up to 1200 degrees Celsius. 1200 degrees Celsius, which is too high. The heat is provided here by an inductive heating, as you can see at the bottom there. It has cooling water around the chamber to reduce the heat from getting the flare. The heat is provided, as you can see from the bottom there. And they tested that on a nickel-based superalloy called MIME 247, which is the alloy that everybody's trying to make by additive manufacturing. And for the first time ever, in 2014, they were able to create crack-free nickel-based superalloy when they used a bed temperature of 1200 degrees Celsius. 1200 is very, very high. So they did create a crack-free build. So people have been saying that probably this is going to be one of the ways by which we can create dense tungsten components if we have access to a heated bed machine. That is actually one of the things that people are hoping to have. But of course, having a machine like this and the machine that can be, stuck for a very long time, and having the material for a long time at high temperature is not a good thing. That's obviously a challenge. Powders, of course, if you keep them for a long time, they will leak oxygen. Even if you have an argon environment, they are going to get the particles to stick together, which can be another problem. So there are issues actually by using this. I am waiting to see somebody successfully printing crack-free tungsten using this approach. Other approaches is electron beam melting. So you know about the RCAM process, as people call it, or now there is also free melt. Both of them can print tungsten. This is a hot bed process. It can generate crack-free builds. The problem here is that because you're using electron beams, not very fine lasers, that the surface finish is poor, and you also have to pre-sinter the powder, so that in order for the process to work. More importantly, if you're hitting tungsten with electron beams, then you're going to get a lot of radiation. So the machine needs to be radiation safe if you're trying to use electron beam melting to generate that. There's only one study that I saw that managed to print tungsten without cracks, and that study is by Jonathan Wright from Sheffield University, who used electron beam technique to print tungsten. And as you can see, this is a section of the build he made, and there are no cracks whatsoever. The part is fully dense. The material, of course, is printed at a very high temperature, and it's a heated bed. So you can control the cooling to a level that it does not induce significant cracking. There's an in-situ stress relief to be able to do that. Again, what else can be done? There are, as you know, beamless technologies that have been coming out in the previous years. So techniques like the FDM type techniques like Mark IV, the desktop metal, or the binder jetting type techniques by XJet, HP, and Stratasys. Those techniques, they are in a sense powder metallurgy technique here in the desktop metal type technique, where you can extrude the powder surrounded by resin, debind, and then sinter. The same is the case with binder jetting. You basically spray the binder and then take it to debind and sinter, and then potentially maybe even hip. The process is good actually. It can create dense tungsten. I've seen some reports from MIT where they were able to print good tungsten chromium alloys, but it has multiple steps. You deposit and debind and sinter, so there's more than one step on them. But as I said, some of the tungsten components, like the one I'm showing here, this is a tungsten chromium alloy. They were able to generate fairly dense parts made using it, and using that process by beamless technology, without laser, without electron beam, only by a sintering type approach. Now, these systems, unfortunately, until now, most of them are closed systems. They are not necessarily for R&D, because you can't really tweak them to be able to play with the parameters or play even with the formulation. What else can be done? Net sheet hipping. So there are people who use hipping like ourselves, where in this case we are blending tungsten with tantalum, or blending tungsten with, in this case, titanium or lanthanum oxides or lithium oxides. Many studies try to use net sheet hipping, and the outcomes of it were quite promising in terms of mechanical properties compared with the alloyed material. So this is something that many people are looking into it, and we are looking into it as well at Birmingham. So in conclusions, choices are limited by material properties and applications. In a sense, if you want to make something for fusion, you are limited in the alloying elements you can try. You are limited even in the alloys you can process. The different materials can be processed. Tungsten, chromium, and moly, we found them to be very difficult to process by lasers, and today I spoke about tungsten in full length. Tantalum, niobium, vanadium are generally very processable. To be able to create a processable alloy, you need to have a clever idea of how you can tweak the metallurgy to give you the right behavior. Alloy design approaches like the one I showed you can generate chemistries tailored for AM and for fusion. If we understand how alloying elements can affect the behavior for additive manufacturing, we might be able to generate dense, crack-free parts in a simple way, actually, in also a low-cost way. Of course, powder quality was an important point, and I explained to you here an example of why sometimes it may not matter if the powder quality isn't great, because we can still get good properties even if the powder quality is not great. We can still good, I would say, good components or functional components without having to have fully dense, crack-free builds. So some of our future work that we are working on, and also with other colleagues, we're looking into in-depth alloy design, trying to use hybrid approaches where we use additive manufacturing together with hipping, and also using hotbed machines like lasers and RChem technology to see if we can generate dense structures using this approach. That's all what I had to say today. So thank you so much for the invitation. I'm very thankful for Dr. Al-Hayni for the kind invitation, and I'll be happy to take any questions you may have. Thank you very much.
Thank you so much, Dr. Moataz, for the interesting presentation. I'm not sure if Professor Al-Hayni is here. Are you still here, Professor Al-Hayni? Okay, thank you so much, and we will be delegating the questions of the audience today. So if anyone has any questions, please let us know in the chat box and we can read the questions. So Professor Habzi has 2 questions. Please go ahead, Professor. Okay. Let's see if I can do that.
Okay.
Sarah, can you from your side? I don't see any.
Yeah, I think Mohammad Reza, can you hear me? You need to unmute people when they have questions. So Dr. Hefsi and after that Dr. Hakshanas, they have questions. Mohammad Reza, can you hear me?
I'm not sure if attendees can ask questions. Maybe if they can write in the chat box, I can answer the questions.
Yeah, currently I don't have any. I cannot from the control panel unmute or mute. I think maybe this is.
I think so.
Just the host can do it.
Yeah.
That is Mohammad Reza. I don't know what happened. Yeah, can you unmute Dr. Hefsi and after that Dr. Hakshanas? Also add Dr. Sujudi to the panelist. I messaged you, but you didn't see it.
How can
I can hear somebody now.
Yeah, just go to view all attendees and find that person and then click unmute. Or make me host if that's easier for you. Right click on my name and change role to host. Then I can unmute them.
Yeah, I can hear. Okay, so I have a question here. There have been many conflicting reports about using tungsten for medical implants. What's your opinion about using tungsten for medical implants, and what are the cost of concept? What is the cost of concept laser system? Okay, the tungsten. I don't recall seeing many reports using tungsten. There are some reports about tantalum, not tungsten, in medical implants. Again, it's yes. I mean, you're right. It's in a sense conflicting reports. Tantalum as an element obviously is very heavy. Its density is very high, and cost is really, really high as well. So it has very limited additions, and it needs to be applied in very specific medical applications. Unlike, for instance, some other competitors like tungsten, for instance, like titanium, which obviously is the main alloy, or the main system that's being used in medical implants. So yes, there are conflicting reports about tantalum, not tungsten. The cost of the concept laser system we have, well, this is a very old machine. We got it a long time ago, but I think the typical price nowadays is around $500,000 approximately, if I'm right. Again, I think in the US they can offer like an academic price. So yeah, I think you probably are tuned to these days. There is a big exhibition called Form Next, which is running online. You may want to see and talk to GE to see how much a machine like this may cost. Okay. Thank you.
So I have a
Yes, hello, can you hear me?
Yeah.
Very good. Thank you so much, Dr. Moataz, for a very nice talk, and thanks, organizer, for having you invited to our seminar. I have a question on mechanical properties of your printed parts. Please feel free to correct me if I'm wrong. If we compare tungsten with tungsten and tantalum printed parts, I feel, of course, the ductility of your tungsten tantalum is way better than tungsten because, of course, these cracks disappear. What about strength? If you have a simultaneous increase in both strength and ductility in your tungsten tantalum alloy, that's great. That's a breakthrough. Can you comment on the strength of your printed tungsten tantalum alloy?
Of course. So it is actually, as you described it, it's an increase in both strength and ductility. The pure tungsten, of course, as you saw, is very cracked. So any loading would result in very poor ductility, and even the strength is very low. Now, the main benefit you get also from adding tantalum, which I forgot to mention, is that having an alloy of tungsten and tantalum resulted in a finer grain size. When solidification happens for an alloy, of course, you do get more nucleation events happening, and you get also a chance to form a much finer grain size, which probably I don't let me see if this was visible on the presentation. The grain size of the as fabricated tungsten, pure tungsten, was very coarse grain, very large grain. As when we started to add tantalum into it, it is probably visible. Let me see if I can share it now. Can you see the screen now?
Yes, I can see something. Yeah.
Yeah. So this is the as fabricated pure tungsten, and maybe I can go to the slide where I showed the ESD, just to give an indication of size. This is the grain size in pure tungsten. This is a 200 micron, and you can see how big the grains are. Massive grains. Whereas after adding the tantalum, I don't have an ESD map here, but you can probably see on the picture there that there is a lot of contrast in the picture. And that's because you have a much finer grain size. So yes, you do get a double win, in fact. Better strength, of course, and better ductility.
Technically, you have this hull pitch strengthening, and you have a simultaneous increase in both ductility and strength. This is great. This is great. Thank you.
Solid solution strengthening.
Solid solution strength. Gotcha. Thank you so much. Excellent. Thank you.
Thank you. Okay, I got a question from good old friend Kivan. Pre-alloy powder. Okay, now, all right. So you see there are a lot of things that are, it's a very good question from good friend Kivan. So there are a lot of issues with, in a sense, trying to print something for nuclear fusion. Now, nuclear fusion, as you know, people have always been saying that when nuclear fusion is going to happen, and the answer is probably in 30 years. This is a joke that people keep saying in the UK, because since the 1980s, every time you ask people who work in nuclear fusion, when will nuclear fusion be available, they say in 30 years. And it's still 2020, and we don't have nuclear fusion. The cost is a great element in nuclear fusion, because in 2020, as you probably know, there's a lot of advancement in non-renewable energy. In renewable energy, I mean. So, for instance, wind energy, solar energy. Now, these types of energies and geothermal energy and so on, they are proving to be actually very low cost and affordable energy types. So, when we think about it, the calculation is done based on pure tungsten, right? When you start to change it into tungsten and tantalum, the cost will increase. When you start to change it into pre-alloy tungsten tantalum alloy, the cost will even go very high. You know that in that case, you have to alloy tungsten and tantalum. Tungsten has a melting temperature of 3,500, which is super high. And tantalum has, of course, the melting temperature, which is a little bit less than tungsten, around 3,200. So it's still a very, very high temperature to create an alloy. Most of the so-called tungsten heavy alloys, they are made by powder metallurgy approach, by sintering them. So no, we have not. It has not even come to our mind to try to make a pre-alloy tungsten tantalum powder because of the cost. The cost would have been, in a simple term, astronomical, and it would have killed the business case for nuclear fusion. If, in order for us to make a tungsten tantalum component, we have to go for pre-alloyed. I think blending, as you can see, it worked out in a very good way. blending of powders does work, especially if you have a good quantity. So if you're mixing 90% to 10%, that usually can give you a homogeneous build and in general good properties, as you saw. Did you try heating the substrate, and what was the temperature range that you tried? We did try heating the substrate. I mentioned to you we can go up to 600, so as I mentioned in our substrate, but that didn't help with pure tungsten. Because the problem with pure tungsten is that oxygen is the main problem here. And even if you are processing it inside a very good chamber where you can have oxygen down to 100 parts per million, you are going to have oxygen pickup and the material will crack. So the problem really is not necessarily the hot bed or the cold bed. The problem is the oxygen. And that's why I was saying that using a technique like hot bed laser may not be the best technique, but using a hot bed electron beam is better, because electron beam, as you know, runs in vacuum. So you don't have oxygen in that case. And that's why, from the work I have seen in the literature, the only technique that was able to print tungsten, which is crack-free, pure tungsten, which is crack-free, was an electron beam technique.
Okay, I have another question about the processing parameter on the machine, on the additive manufacturing technique. To how extent you believe that optimizing these process parameters can improve the the output printed material of tungsten, pure tungsten, or other tungsten with other alloying elements?
It is obviously an important factor. The process parameters, you see that tungsten has a very high melting temperature. So you need to go very slow. You need to go very high in laser power. But to be fair, in my view, this is a case where we cannot blame the process parameters. We have to blame the inherent properties of the alloy itself, or the material itself. Tungsten hates oxygen, hates small amounts of oxygen. Even tiny amounts of oxygen are enough to get the material to crack. So although, yes, you need to optimize the parameters to get the right heat input, to get the right amount of the right temperature in order to melt the material uniformly. But to be fair, the bigger problem that you are faced with is oxygen. And it's not even that I have seen before in papers, people used different parameters to create different levels of oxygen pickup. That's true. So in additive manufacturing, for instance, if you go slightly hotter, you are likely to result in more oxygen being absorbed by the material you are melting. Whereas in this case, any small amount of material, any small amount of oxygen you suck is going to kill the material. It's going to make it even further embrittled. So again, the bigger problem is the oxygen rather than the parameters in the specific case of tungsten.
Thank you.
Nothing.
Hello, Dr. Moataz. This is Hossein Sajidi. I'm sorry I joined late, but I'd like to thank you for basically delivering this interesting presentation. I was basically able to listen to half of the documentation.
I can't hear you clearly, Dr. Sajidi.
Sorry, I was just speaking a little bit slowly, so
yeah.
I was just thanking you for your great presentation, and appreciate for doing this.
No, that's great. Really happy to talk to you. I'm looking forward to do more collaboration with Dr. Elhania and colleagues at Toledo, and hopefully when things improve, hope to visit Toledo in the near future.
That would be definitely great. And I am basically switched to panelists, but I still don't have quite the same things. Sarah, do you mind to double checking? And I thank Allah and Muhammad for their help. Do you mind checking if we have any outstanding questions in the Q&A?
Yes.
In the chat box?
There's one more question, which is about amount of sampling, again from Muhammad Reza, on the amount of tantalum. We've gone for 10. I've seen papers that have gone down to 5, and they had some residual cracks. So the first report we saw was 5%. So we decided to go to 10%. We have not changed the tantalum that much. I think the 10% we were restricted by two factors. One of them is the design. So people who design the nuclear fusion reactors, they tell you we can go up to a maximum of 5.9%. You know, they give you a number, and in this case they said don't go above 10. So we decided not to go above 10. The second thing was that the cost for them as well, because they essentially do their business models based on how much material you're going to add. Now I mentioned that the cost of a kilogram of tungsten is something like 50 pounds a kilogram, whereas the cost of tantalum is probably like 500 pounds a kilogram. Tantalum is very expensive, by the way. It's at least 10 times potentially the cost of the powder, of the tungsten powder. So that's why we got stuck at 10. But we saw there are reports that looked into 5%, which was insufficient to eliminate the cracks completely. How can modeling? Yes, okay, very good question. How can modeling approaches improve the alloy design or additive manufacturing? Yes, that's a very, very good question. In a sense, we have a huge palette of materials and of elements, I would say. So there are other elements which are allowed to use. So tantalum is allowed to be used. We can probably add titanium, we can add yttrium, we can add rhenium. And if you look into the majority of tungsten, because of its very high melting temperature, the number of alloys that we have are rather limited. They are only, like most of them, are either binary alloys or ternary alloys. So there must be a better alloy that is probably more complicated. The design of alloys, as you know, the more you have more alloying elements, you end up generating a good or a stronger or a better alloy. Like if you take, for instance, nickel superalloys as an example. Nickel superalloys, as you know, are super complicated in their chemistry. You have nickel, niobium, tantalum, hafnium, aluminium, titanium. So, and each element is there for a purpose. Aluminium and titanium for gamma prime, certain elements for oxidation resistance like chromium. And this is essentially what can help us generate a super refractory metal, or super refractory alloy. If we use alloy design approaches, whereby we can generate a lot of data, first of all, from different alloys, and then use a good computational technique, something like machine learning. If we combine that with also thermodynamic modeling, that will even be better, so that we can alloy design a super tungsten alloy that can handle all the factors we spoke about. It becomes processable by additive manufacturing, has high mechanical properties, has very good ductility. So that, I think, is the next thing to try to design a stronger tungsten alloy. Okay, we got another question from Amir about the mixing. Yes, how did you mix them, and was the product of mix uniform? Mixed tungsten with Inconel, but I couldn't get the uniform mix of the two particles. I used ball milling, not other. Okay. We used the blending was uniform, and it's interesting that you mentioned about this subject about mixing. I don't know if you noticed in my slides. I think I'm sharing now my slides. Yeah, I'm not sure if you noticed that you can see here on the figure the difference in size between the tungsten and tantalum. We used very small tantalum and very large tungsten particles, or not very large, I would say, fine tantalum, large tungsten. And the reason for that is from our experience on blending. If you are blending big, if the alloying element that you're adding has particles which have the same size as the parent particle, then you may have sometimes some issues with homogeneity. So in our case, we did the blending in such a way that you have fine tantalum to fill the gaps between the large tungsten. Essentially, it's just tubular blending, so they were blended for roller mills. We didn't keep any special blending, just simple blending, and that was sufficient to allow us to get a homogeneous mix as you saw in the results. Okay. Back to questions. Chat box. Yeah, the problem with ball milling is that sometimes ball milling can sometimes flatten the particles, and it can affect the powder morphology. So we never use for the SLM work, for the powder bed work we do. We actually rarely this problem really. Yeah, essentially the ball mill usually flattens the particles and can affect the morphology, which can affect their flowability in the powder bed. But was the tungsten tantalum alloy used for medical implants or medical scaffolds? I don't think so. I don't think so. Tungsten in general is very high temperature applications. I don't recall honestly that it has been used for medical implants. I hope I haven't forgotten any questions.
Dr. Qattawi, are any of the questions left? Because
no, I think I handled them all.
Yeah, I already asked my question. Thank you.
Thank you very much.
Okay, thank you.
Thank you very much. Our speaker basically did both the speaking and moderator. I really appreciate it. I'm sorry if that wasn't inconvenient.
Thank you very much for the time, and hope to see you all very soon. Okay, stay safe and have a nice weekend, everyone. Okay.
Thank you very much. You too.
Yeah, talk to you soon. Take care. Bye bye.